Okay, so we're in the second part of section 4 today, chapter 9, section 4, day 2. We're going to continue the same kinds of things we did yesterday. We're going to solve equations by factoring. Yesterday we learned that when you set an equation equal to what number? You remember? 0, good. We find the r's. What are those called? The roots. Okay, good. So the roots are also known as the solutions. So when you're solving, you're getting solutions. And solutions are also the roots of the equation. Okay? So we're going to solve equations by setting the equation equal to 0. Now here's the first equation. It is already equal to 0. We don't have to transform it to set it equal to 0. There it is. 3x squared plus 18x equals 0. You just showed me that your factoring is good. We're going to factor this. What is the GCF of these two terms? What can I pull out of 3x squared and 18x? Both. Selena? What? 3 and x. Good. So if I pull out 3x, what would I multiply it by to get back to this term? 1x. And what about this term? 6. Good. So there it is, factored. So our first step to finding solutions is factor. And now how many factors are in this new expression here? How many terms are being multiplied together? Big factor. Good. Summer, say it. 3. We've got 3 times x times this binomial, x plus 6. Okay, so there are 3 factors. So the question is, using our zero product property, what could make these factors 0? Could we make 3 0? 3 is a constant, so it just is 3, so we can't make it 0. Could we make x 0? We could just say x equals 0. Good. So one solution would be x equals 0. And then when we look at this binomial, what would allow that entire binomial to equal 0? Good job, negative 6. So we have 2 solutions here, 0 and negative 6. We can also call these the roots of the equation because they are the zeros of the equation. Okay? So the next step would be to maybe transform an equation before we factor it. That's what this says. Set your equation equal to 0 first if you're going to find the solutions. So we might receive an equation that is not already equal to 0. 4s squared equals 14s. How might we transform this so that it is equal to 0, Tara? You could? Okay, good. If you did, you would have what? So very good. So she says subtract 14s from both sides and you end up with an equation equal to 0. Okay, what would the next step be? Andrew? Good, so you want to factor it, and he says the GCF here is 2s. So what would be the binomial then? 2s times what equals this? 2s times 2s, okay. So, and then 2s times what equals 14? 7. So we have 2s times, can you say it? 2s times 2s minus 7. There it is. So we now have our factored equation. And we have, again, how many factors here?
3.
3 total factors. Good. We have 2 times s times 2s minus 7. So what would one of our solutions be? 0. S equals 0. Good. That's the first one, right? And now you might set 2s minus 7 equal to 0. Some of you are good at doing this just mentally, right? But we're going to end up adding 7 and then dividing by 2, right? Both sides. And so your answer would be S is, you could say 3.5 or 7 over 2 or whatever. Okay? Good. So we have 2 solutions once again. Okay, so once again, pause the video, try these, and come back and see what answers we found here, what solutions we found for these three. Okay, so the first one, Michael factored out an A, and we have the solutions of 0 and -5. The second one, Tara factored out 3S, and we have the solutions 0 and 3. And the third one, Kelly transformed the equation so it was equal to 0, and then found the solutions after factoring of 0 and 1/2. Good job. Okay, so here's the next type of question you might hear. And the question would say this: find the zeros of the functions. I would highlight this in your notes because when it comes to the test, you'll be asked to find the zeros of the functions, and people will say, well, what does that mean, Mrs. Smith? Yeah. And we have gone over this. You can see we're doing it today. Finding the zeros of the function means what? What does it mean? It means find the solutions, find the roots. So what are we going to set equal to 0 here? Dina, say it. F of x. But what would be a common error? Plugging in 0 where? For x. Okay, that's not true. Okay, so if you're asked to find the zeros, we can change the equation. We know this is a way to name an equation, f of x. We know that f of x would be equivalent to the output y, right? So change it to a more familiar form. And if f of x equals 0, then that means y equals 0. Okay? And so now you're right on track to do what we've done. The equation is set equal to 0. The problem will be, please take the time to read your the directions for each of the sections as you're doing your assignments so you understand the terms being used. During a test or during an SAT or whatever, if it says find the zeros of a function, you can't ask at that point. You have to be familiar, so please highlight this. This is not used as often as find the solutions. That's more often used, right? But this gives you the cream of the crop person who knows, oh yeah, that just means set the equation equal to 0. So, Talia, do you want to tell us?
I'm confused.
So, if you are asked to find the zeros of a function that's written in function form, you simply set this function equal to 0 as we have done here. That's all you do, and then you proceed through what we've done. So you would factor this. What's the GCF here, Talia? 5 and, what else do they both share? 5x. So when you pull out 5x, what do you get? 5x times
5x
plus
3.
Good job. There it is. And so do you want to tell us the solutions?
X equals 0 and -3.
-3 over,
5.
you would subtract 3 and divide by 5. Good. -3 over 5. Oops, it's not there. Okay. So it should be, if the second one is 5x plus 3 equals 0,
It's always 0.
you would subtract 3 from both sides and divide by 5. So -3 fifths. What is -3? Who can tell me quickly, what is -3 fifths as a decimal? It is? Good job. -0.6, right? 0.6. Excellent. Okay, see if you can find the zeros of this function. Find the zeros of the function. How did you set this up, Dina?
Y equals 6x. Well, 0 equals 6x squared.
0 equals 6x squared minus 20x, she says. And then how did you factor it?
2x open parentheses 3x minus.
Good job. 2x times 3x minus 10. And your solutions are?
0 and I didn't do that part yet, but 0
and when you have this set equal to 0, you would do what? You would add 10 and divide by 3. So you would have 3 and 1/3, right? 3 and 1/3, okay? Or 10 over 3 is not turned into a mixed number. It's improper. In math, we prefer to have 3 and 1/3 to 3.3 because 1/3 is not rounded, right? 0.3 would be a rounded number, which isn't as precise as a fraction, okay? Now we're going to use the vertical motion model. The vertical motion model is is to quadratic equations as what is to linear. What's the most, remember I told you the most common linear equation used? Well, I believe it.
Y was MX plus B.
Well, no, that's the model of a linear equation, but what's the most common everyday one that's used on graphs? D equals RT, dirt, right? The distance formula, or a rate formula, depending on what you're talking about. It's such a commonly used linear equation. So we did a lot with D equals RT back in linear. We're now moving to quadratic where we have x to the second, okay? And so this is the most common quadratic equation. It has to do with falling things or thrown things, okay? It's called the vertical motion model. And it's the model for finding the height of something that has been thrown or projected out there, shot, whatever you would say, okay? It could also help you find the time it takes something to land and things like that, okay? So we will say that the height of a projectile equals negative 16t squared. There's what makes it quadratic. We're squaring an input here, plus vt plus s. So write the model down and then let's talk about these different terms. The h is the height of whatever it is. So imagine I'm shooting a basketball. It's the height of the basketball at any particular moment in time, t. T is time. In seconds. That's in seconds. Now, if I shoot a basketball, I can vary the v. What is the v? Velocity, right? The initial velocity I throw into it. The other thing is, I could vary the s, which is the starting height. So I could shoot a basketball from the court, or I could go up in the stands and be like above the basket and shoot it, right? Or I could somehow dig a hole and, shoot it from below the court level or whatever. So the starting height can vary. The negative 16 is, it's negative, right? Okay, so it's pulling on whatever has been projected. So if I shoot a man out of a cannon, like at the Del Mar Fair, sometimes they shoot a man out of a cannon, right? What is pulling down on him? Gravity, there it is, that's gravity. This negative 16 t squared is the gravity component, okay? Now, if I shot somebody out of a cannon, I could shoot them and they could just plop right out the end because the velocity was really minimal, right? Or I could give them a huge amount of force. So this is going to really affect the height that they travel, right? Yeah. Now, of course, the way you point the cannon will affect things, like a line drive versus a hop, high fly. Some home runs are kind of like line drives, and they have such a velocity that they make it over the fence, and some are just really bombs out there, like Barry Bonds would hit it into, over Candlestick Park and into the bay. And so people would sit out there in kayaks and wait for the balls to fall. So we're going to use this in one example here. So read the example. Okay, so this little spittlebug jumps into the air with an initial velocity of 10 feet per second. So we're going to write an equation that gives the height of that spittlebug as a function of the time since it left the ground. So we're going to use our vertical model. Okay, a vertical motion model, which each time you're facing a problem like this, write it down so the model becomes really familiar
Negative
to you.
16.
H equals negative 16 t squared plus vt plus the starting height. Okay, so we have some information that could be used in this model right now. What it has been given that we could substitute. Lauren, where do we put it? Good, so we're going to put 10 here, 10 feet per second. We don't know the time.
Does it say?
And so write an equation that gives the height as a function of time since it left the ground. What is the starting height if you're leaving the ground?
Zero.
Zero. So look at, we don't need to even include plus 0. We could put plus 0, but we don't need it. So there you go. You have, all we need to know is how much time. After 1 second, we can say right now how much, where this bug is. After 2 seconds, we could state the height of the bug. And we could find out when it hits the ground again or whatever. Okay, we could graph this. So it says here, the spittlebug reaches its maximum height after, look at 0.3125 seconds. So how high can it jump? What will we do, Michael?
You would plug 0.3125